So hello again and welcome to the second video lecture on Integrodifferential Equations. Now what are these? Let me give you a very quick example. Consider an RLC circuit. Take an RLC circuit on which we apply an external voltage that we can manipulate. We apply the input variable V, and we want to study the dynamic properties of the current I that flows through the circuit. The equation that describes the system is the following. And we can see here that we have the current, we have the derivative of the current, and we also have the integral of the current. Such equations that involve derivatives as well as integrals are called integrodifferential equations. The question is, can we write these in the very nice form of a state space representation? And the answer is yes, we can. But before we get there, we need to give some mathematical background. So I will first give the definition of an antiderivative. The antiderivative is for the derivative what multiplication is for division. In other words, let us give the definition. Take a function f from R to R, which is so that there is a function f uppercase, again from R to R, which is differentiable so that the derivative of f uppercase is equal to f lowercase. Then function f uppercase, kind of the inverse of the derivative, right, is called the antiderivative of f. Just a few examples. If you have function f of t, which is equal to 1, then what is an antiderivative of f? It is this function, f uppercase, let's call it f1, which is equal to t. Indeed, if you differentiate f uppercase subscript 1, you will obtain f lowercase. Then f2 of t is equal to t plus 2020. This is an antiderivative of f lowercase as well. Well, actually, whatever you add here for every constant c, all these will be antiderivatives of function f lowercase. One more example, take function f of t be equal to t. Then function f uppercase, which is 1/2 t squared plus 2020, is indeed an antiderivative of f lowercase. So I hope you get it. Now we have defined the antiderivative. There is a very intimate relationship between antiderivatives and derivatives and integrals as well. And this is given by the fundamental theorem of calculus. The fundamental theorem of calculus gives us two very important results. One is how to compute an antiderivative, and the second result is how we can compute integrals using the antiderivative. So the first one goes like that. Take a function from an interval a to b, closed interval a to b, that is real valued, which is continuous and differentiable in the interior of this interval. Then we can construct an antiderivative. Let us write it down. So take a function f from ab to r, which is continuous on ab and differentiable on the interior of ab, or on ab open. Then we define this function f of t is the integral from a to t f tau d tau. Now this function is continuous, it is differentiable, and it is an antiderivative of f lowercase. So f uppercase is continuous on AB, it is differentiable, and most importantly, it is an antiderivative of f lowercase. let's write it a little differently, equivalently. Let's write the following. So what this says is the following formula. I'll write it here. It is that the derivative of the integral from a to t of a function f is this function f at point t. This is what the first part of the fundamental theorem of calculus says. Now let's write down the second part. Now the second statement of the fundamental theorem of calculus says that if f is integrable on AB, this means nothing but if the integral from a to b of f exists, okay, if the integral of f from a to b exists, then the integral, this integral, is equal to f uppercase of b minus f uppercase of a for any antiderivative f uppercase of f lowercase. Okay, so this is the fundamental theorem of calculus. Let us now apply it to write the equation that describes this RLC circuit in a state space representation. So I'm going to erase these, but you can take notes in the meantime. The equation I gave in the beginning was Ri plus Li dot plus 1 over c integral from 0 to t I of tau is v. So the trick we'll do here is really reminiscent of what we did last time for high order differential equations. We will define a new variable for this integral. Let us call it simply z. It will be z of t, function of t, is the integral. Now note here that if we differentiate both sides, if we apply the derivative, we obtain that the derivative of this, derivative of z, is the derivative of the integral. But you have the formula right here from the fundamental theorem of calculus, and it says that the derivative of the integral, it's like to write it simply, okay, just don't tell anyone I did that, this is not very rigorous, but the derivative of the integral is equal to the function. So we have equivalently z of t derivative is equal to I. So this is a differential equation. However, you see here that we have that this implies that it is not however implied by this part of the equation. So if two functions have equal derivatives, does not mean that the functions are equal. To make this equivalent, we have to append here a little condition. And this condition is nothing but the observation that z at time 0, if I plug in 0, I will have the integral from 0 to 0 of the current, and this will be equal to 0. So now this initial condition goes hand in hand with this differential equation. The rest is very simple. So I will take the given Integrodifferential equation, I will write it down again, Ri plus Li dot plus 1 over c, and instead of the integral I will write there the new variable z. Equivalently, this is now, it looks like a differential equation, it only has a derivative. I will move all terms that don't have a derivative onto the right hand side, and I have and this is my differential equation. However, note here that on the left hand side we have I, on the right hand side we have both I and z, which are variables of the problem. However, z itself satisfies this differential equation. I will write it just below, I will copy it just below this equation. Don't forget about that, we have to write this as well. And now I have this system of two equations. It should be evident that the state of the system is I and z together. And to save some space, I will just wipe out the circuit over here, make space on the whiteboard. So the derivative of x, which is the state variable, so I dot z dot, is nothing but however, don't forget about the initial condition. Z0 is equal to 0. And there you go. This is the state space representation of this integral differential equation. Thank you very much for watching, and goodbye.